So, welcome to episode 2 of CircuitTV, and in this second episode what we're going to be talking about is servo motors, kind of going into stepper motors and their applications and some different things that you can do with them. So you may have seen a couple of the recent projects that we did, a couple of them over at ASU where we did first this breadboard battleship, where this is actually 2 servo motors controlled by potentiometers, and then we strapped it all together and it made us able to aim and then fire a laser, and we lined up a couple of them and we did battle, and that was really fun. Students over at ASU seem to really like that project, and you can find that build over on our blog, circuitspecialist.com/blog. Another application, this is the robot arm designed by our friend Kang Win, and this actually features 4 different servo motors, and you can position this arm, turn it, as well as open this grabber, all controlled by servo motors and an Arduino. So a couple differences between servo motors and stepper motors. Servo motors have a relatively flat torque curve. They're better for high-speed applications such as positioning a robot arm. Most of the time they're going to be limited to a certain amount of turn. So you can see this goes from lock here to lock there. As in contrast to the stepper motors, where the stepper motors, they have many more steps and they have a better torque at low RPMs. So they actually, but they all go 360 degrees, and because of the additional steps, they're a little bit more precise. So a stepper motor would be more likely to be found in something like a CNC machine. One thing that's different with the servo motors is they actually have a response circuit that sends back feedback from the motor to give it awareness of its position. So when you're using them for, say you're doing an Arduino build, like we use most of the time, they can actually be aware of where they're positioned and send feedback to the Arduino to do different kinds of applications. So what we're going to do now is we're actually going to show you how to program a servo motor with the Arduino, and we're going to take you over to Josh, and Josh is going to walk you through that entire process. So over to you, Josh.
Hi, my name's Josh. Just coming here today out of Circuit Specialist. Cody's already told you a little bit about what we're talking about. We're talking about servo motors today, and I'm going to give you a little brief crash course on the programming aspect of it. I don't know how many of you are familiar with Arduino, but Arduino is basically a programming platform that you can use. It's really great for object-oriented programming, using things like stepper motors, servo motors, LEDs, putting using actual physical objects instead of just computer abstract applications. Today we're talking about servo motors, and I have this little SG90 from our website, circuitspecialist.com. You can find that there. We'll be using the Arduino Uno R3, and today we are going to start off with the Arduino Sketchpad. And first of all, you could go ahead and open up your examples, go straight down to servo motors, and you already got 2 functions. The sweep function is one that we're going to be taking a look at first, just to try to give you guys general concept. All right, if you look inside the servo function, it'll basically tell you what to use, where to attach things, basically where to plug in pins. On these specific servo motors, you have a orange, a red, and a brown wire. I always remember brown is for ground, red is your hot. It's a pretty common thing that you know. So we'll be using a small breadboard that we also sell here at Circuit Specialist, and we'll be plugging into our Arduino, and we'll hook one side up to our ground and one side up to our 5-volt, just so that we have power distributed to our little breadboard. And if you notice in this function, we have position position 0, that's basically telling us that our position is starting off at 0, 0. That's the variable that we're storing. Now my servo.attach shows that we'll be on pin 9. This is on the digital pin 9. I'll get a little more into what these attach functions and map functions and write functions actually mean when we start developing our own code here in a second. But as of now, we basically just connect things. So we will connect our red to our power distributed for our 5 volts, and we'll connect our ground to ground like so. I don't know if you guys get a clear shot of that or not. And we will use our control wire, which is the orange wire on the stepper motors, to plug into pin 9. As you can see, it says that we'll be using pin 9 on the screen right about here. So what we'll do is we'll verify the code, just compiles the sketch. If any of you are familiar with C++, this is, like I said, very familiar with object-oriented programming. You have a name, library functions that you're using, your object, and then the pin that you're actually going to be putting it on. So sometimes this takes a little bit, especially when we have other things running on your computer. But I've verified this, it's a project function before, so we're going to try to upload it as soon as it's finished. There we go, it looks good, upload. And what this function is supposed to do, I'll actually tell you right in the beginning. It'll create a servo object, and it will actually just allow the servo motor to sweep 0 to 180 degrees. You can see it'll sweep, immediately rotate back to 0, immediately rotate back. And it'll continue a sweep function. Basically, this could be used for, you can adjust the time delay in here. We have a delay of 15 seconds before it does it. If we adjust this time, we can actually get this to move a little bit slower. Should be able to get it to move a little bit slower. And you could use this kind of function for if you say have set up some kind of automated home recording system and you want a camera to act as a sweep function left to right, just scanning your backyard, front yard, music studio or something. So as you can see, it's going a little bit slower. That way you are not just like getting seasick from moving all over the place. But what we're going to do right now is talk a little bit more about the actual functions inside this servo library. So you use #include servo, #include, and the brackets servo.h. And I'm going to go ahead and start a new sketch, so that way we could take a look at it. And they have these loops and stuff set up, but I'm going to go ahead and delete it. And this will just keep rotating. The thing with the Arduinos is it runs a continuous loop. It'll continuously do what you tell it to do until you tell it to stop. So that's always something to think about when you're programming is it's going to keep doing it forever. So we'll start off with including your stepper motor library, and that's using the #include bracket servo.h. And this actual function that we're going to be writing, or this program that we're going to be writing, is very analogous to the knob function that you can actually find as an example inside the sketchpad. I just figured we'd write it out to explain a little more. So the next thing you're going to do is we include the servo library, and there's multiple function calls in there. One of the first things you'll do is you'll have your object, which is a servo motor. Sorry, punctuation counts. Servo, and then we will call it Circuit Specialist. Servo. So that way you go ahead and assign a name to it, and we'll just add some comments. Name the servo. It's always good to add comments when you're programming so the person behind you knows what they're looking at. Otherwise it gets a little confusing when you have hundreds, thousands of lines of code. So the next thing we'll do is we'll initialize a potentiometer. What we're going to be doing is using a potentiometer to control the position of the stepper motor based off reading the wiper between the positive and negative terminals on the potentiometer, reading the value that it is, and assigning that or mapping out a function between 0 and X number. I believe it's 1023. And that will give us a position to move the servo motor between 0 and 180 degrees. So we did this before, our breadboard battleships. We taught a class actually over at the Arizona State University for the IEEE members, the engineering club. And what this is, it has two potentiometers, we have a laser diode on it, and we set up these servo motors. One has an x-axis, and y-axis. And we went ahead and played Battleship. It's a really simple code. You can find that out on our blog, www.circuitspecialist.com/blog. You can find the code there and the whole build. It's actually a really cool project. But anyways, let me get back into this. We'll call this potentiometer. And this is going to be the pin that we're going to set it at. So we'll set this as pin 0. And like I said, give you a little bit of comments for the next person. Yeah, there we go. All right, then we will give it a value. And this is just the first value that's going to read. So that way you are actually giving it a name. Void setup, standard setup loop, and we will keep those as empty brackets, just something you got to do. And we will call our, next thing we'll do is call our object, the one that we use, Circuit Specialist Servo, and we will use an attach function. So now let me get a little bit more into the functions that this servo.h library entails. You have an attach function, which is basically the easiest way to think about it is you're attaching the servo motor to that pin. So you'll write the name of your servo motor, because you can have multiples, so you can have ones that are named different things, and you write dot attach, and we'll equal sign, and we actually not equal sign, sorry, wrong syntax. Open brackets, and then we'll put it on a pin. So we'll put it on pin 9. Put it on pin 9, and close it. And that will be in our setup. So that way we go ahead and we're saying that we're using pin 9 for this servo motor. That'll be the control wire from the servo motor is hooked up directly there. And it's, like I said, we're using pin 9 right here. Then the next thing you'll do is you'll create a loop function. And this is what's going to keep on repeating in your code. This will keep on repeating over and over and over until you decide to write a new function to your Arduino. So we will say value is equal to analog read, and what did we call it? Potentiometer. So what we're doing here is basically we're reading analog read potentiometer, close that. What we're doing is reading the value that we're going to have, and we are going to basically get a value and we'll store it underneath that val variable. Then the next thing that we do, which is really cool for this servo motor library, is a map function. And what it actually does is it takes 5 parameters, and it basically relates them to each other. So the first, it's always in order. So the first function that you use will be our value that we read. And then the next function will be, or the next variable will be 0, or next parameter, I'm sorry. The next parameter will be 0 and 1023, because that's the way that the Arduino reads it. I believe is it binary? To the power of 2. I forget how to explain it, but you read between 0 and 1023, And then what we do is we figure out what we're going to map it to. We're going to map it between 0 and 179 because that would be 0 and 180 degrees for our stepper motor. So we'll close that off. Then we will write we'll use our servo motor again, and we will actually write the value that we read there earlier. And what did we call it? Val. Close, and then you have to put a delay for how long it will go before it repeats the loop and repeats the loop. And this is in milliseconds, so you got to remember that. This is 15 milliseconds, not 15 seconds. So, so what, about 1/8 of a second, a little less, 1/9. And we shut that off, close our brackets, and we should be good to go. So we'll verify this. Oops. I'll save it. Cool. Verify it, make sure it works correctly. And okay, there's an error compiling. Compilation terminated. Verify. Exit status 1. Error compiling for board. So this is one thing that's great about programming is you make mistakes and you got to figure out where they're at. So we have our pound include servo.h. There we go. That should work. Like I said, punctuation matters. Every capital you use has to be capitalized again when you use it again. Every time you call a library function, you have to use, the correct syntax, the correct punctuation. So this should work now. I believe that was my only mistake. And we'll actually start pulling. We said that pin 9 will be our servo motor. We said that our potentiometer, let me see, I have a potentiometer around here, will be the center pin on the potentiometer will be used for analog pin 0 because that's what we're reading at. So we'll plug this into pin 0. And then we're going to tie the other two between our negative and positive. So that way we have we're basically reading the difference in resistance between the 5 volts, between the ground and the 5 volts. So let me upload this real quick. So as you can see, it checked out. That's good. That means our code looks good. There's nothing wrong with the programming. As long as our board's hooked up correctly, this should work fine. We have our stepper motor on the control on pin 9. And as you can see, we have this right here. And if I turn the knob, it'll rotate to the right. We turn it to the left, it'll rotate to the left. It's a little jumpy. We found out before that by using the current supplied by the Arduino board, you actually have some fluctuations which will cause it to jump around. A good way to eliminate that is to get a regulated 5-volt independent source, and that way that'll help you stop all this jitter. So like I said, we've done this for the breadboard battleships. We also did a laser alarm code. We've done some really cool things. We've actually incorporated it into a remote control device so that way you could, from a distance, control a stepper motor, or servo motor, excuse me. So let me talk a little bit more about the functions. We talked about the attach function. We talked about the write function. What the write function does is it writes a value in degrees to the stepper motor for servo motor for the position. So basically 0 is all the way in one direction, 180 is all the way in another direction, and 90 is basically no movement. So when you start it off, you'd start it off at 90, you would have no movement. That's a good way to go. There's a write milliseconds function, which basically takes the value in milliseconds, and it sets an angle relation to this on the shaft. So 1000 will be counterclockwise, 2000 will be full clockwise, and then 1500 will be mid. But since some servo manufacturers don't actually adhere to this standard so well, you'll find ranges between 700 and 2300 for your real values. It's okay to play around with it. If you hear a grinding noise or a grrr at the end, that means that you're going too far that way, so you might want to reduce your parameters a little bit. We talked about the read function. What that does is read. Actually, we talked about analog read. What the read function does in the servo motor library is it actually reads the position of the stepper motor, of the servo motor. I keep saying stepper motor. What it does is reads the position of the servo motor, and it'll relate the amount in degrees back to you if you go ahead and serial print it. Then we have attached, and that's a true or false statement. So you could say if circuit specialist servo is attached or dot attached, it'll return a 1 for true and a 0 for false. So that's a good way to use your if and statements or if else statements. And then we have a detach. You can detach your servo motor if you want to eliminate it from using that pin.
Okay, Josh, thank you for that explanation of the embedded control version of the stepper motor controller. One of the beauties of electronics is that there is no one right way to do anything, and that's what engineering and DIYers are lucky in, that they have a myriad of options available for to produce the effects that they desire. This episode is talking about stepper motors and how to control them. And so we're going to explore a little different variation of a similar circuit, but it's actually quite different, but the results are exactly the same. This circuit uses a 555 timer, which is a discrete level version of the circuit, whereas Josh's version relied on firmware and a little bit of computer programming, code writing requirements to obtain the results that he desired. We're going to do the same thing, but completely in hardware, so there's no code writing required. This one requires a few more parts, but again, the results are identical. What we're using here to control the stepper motor is a circuit based on a 555 timer. The 555 timer is a circuit that's been around for many, many years and is probably one of the most ubiquitous circuits ever developed. Any hobbyist is familiar with it. It's been around for, I could say, since pretty much early electronic days, and is just useful in so many different applications. In this particular application, we're using it to produce various pulse widths. And if you remember from the explanation of how a servo motor works, a servo motor determines what direction it will rotate in based on the width of a pulse that's being fed to it. So while we did this in software or in firmware in the previous version, we're going to do this in hardware using capacitors and resistors to produce this variable pulse width. We found from the specs of the servo motor that any pulse that is half a millisecond wide will turn the servo in a complete anti-clockwise or counterclockwise direction. Any pulse that is 2 milliseconds wide will turn it in the clockwise direction, again to the extreme limits of the mechanics of the servo motor. So this circuit here that we're using uses a capacitor and resistor to produce these effects. Now, we talked about capacitors in a previous version of CircuitTV, a previous episode, and so I'll jog your memories a little bit. A capacitor is used to store charge, and in this particular application we are charging up the capacitor to the full voltage of the power supply, which happens to be 5 volts, and then we're using the resistor to discharge it, and the pulse width that's produced is determined by the size of the resistor and ultimately how long it takes to discharge that capacitor back down to a very low voltage, very close to ground. So we have this potentiometer here that will give us the ability to vary this pulse width. The output of the 555 timer is connected directly to the servo motor, and I do have on this oscilloscope the display of what the pulse width looks like. Now, since this is a new setup here, notice that the signal is jumping around a little bit, so I want to first of all adjust the controls on this oscilloscope. By the way, this is a Handtech DSO 5202P oscilloscope, which is available from Circuit Specialist for much less than any of its competitive models that are very, very similar. This is available for less than $300 from Circuit Specialist. It's a 200 megahertz bandwidth scope capable of displaying pulses, RF signals, audio frequency signals, and in our case, this varying pulse width signal is used to control the stepper motor. So I'm going to adjust the triggering first to try to make this pulse a little more stable, to kind of get it to stay still so we can look at, get a better idea of what we're doing. I'm also going to crank the width up a little bit just so we can see the individual pulses. And I'm going to adjust the position here just to get 2 good cycles of this pulse train so that we can note the variation of the pulse width as I vary the potentiometer. Now I know the motor may be a little hard to see, but as I adjust this pot, so right now here we're on 2 milliseconds per division, and it's probably pretty impossible to see the graticules on the scope, but that is pretty much 1 full division, so that's about a 2 millisecond pulse. So that right there has caused the servo to rotate completely in a clockwise direction. If I now turn the pot in a clockwise direction, it now causes the servo to rotate in the complete opposite direction. Notice how the width of the pulse changed significantly. So now we're at about a 1/5 of the 2 millisecond division. So that's pretty close to about the 1/2 millisecond pulse width required to make this servo rotate in the counterclockwise direction. So again, I'll demonstrate that one more time. Notice the very narrow pulse width. In fact, I can crank this width up a little, we can get a better idea. We're now at 0.8 of a millisecond per division, and we do have just slightly over 1 division, so we got again probably just a little over probably 9/10 of a millisecond. So that's close enough for this servo to detect that as a the control signal that it's required to rotate in the counterclockwise direction. I'm going to go ahead and adjust the pot now so we can watch the pulse width change. And there it is, all the way out. And now we've got, again, at 0.8 of a millisecond, we've got 1, 2, 3, about 3.5 divisions, which is real close to the 2 milliseconds required to rotate in the clockwise direction. So as you can see, this circuit here requires a few more components than the Arduino-based version of the device, and of course the wires are a little more messy and spaghetti-like looking, but it does the exact same function. So we've just demonstrated now 2 different methods of building a circuit that will control the servo motor. Now the servo motor can be used, it's used quite a bit in hobby RC electronics to control the rudders or steering on RC cars or RC planes or RC boats. We built a circuit here at Circuit Specialist to open and close a deadbolt on our doors here, so we completely automated the locking and unlocking function of our doors. So a servo motor has quite a few uses, and they're basically limited only by your imagination. So again, I want to thank you for your time, and hopefully we've been able to teach you something today. And I guess we're off to Cody.
Just wanted to come back and say thank you very much to everybody who's joined us on this second episode of Circuit TV. This is live. We are recording here right in our studio. So we definitely appreciate you guys sticking with us through the technical difficulties and any kind of latency issues. We're doing our best to make this stream as high quality as possible and to get everything solved, but we are doing it in real time. So thanks again, everybody, for joining us. My name is Cody, joined here by George. George is our in-house electrical engineer, and Josh. Josh is the guy that answers your phone calls and helps you out and helps you select the parts you need for your project. So feel free to call us anytime. Make sure you check out CircuitSpecialist.com. Check out our blog. We're on Facebook, Twitter, and YouTube. So please see the cool stuff we're sharing, and hopefully we'll be able to help educate the community. So thanks again. Have a nice day, everybody.